Okay, do you hear me now? Yes, okay. The microphone was switched off. Okay. So, and you see my screen also. So just I want to mention some two or three points before we go to the slide. First is that I find it that the showing the slide and talking about them and doing some calculations at the time with Mathematica is a good idea. So I always do like that. So every lecture I will do some calculations. And of course, before the midterm, we will spend one lecture at least to talk about the questions and problems and those stuff. Second is that I meet one of you, and today she asked me about the textbook. As I mentioned, this course before in the last semesters, previous times was based off the lecture notes, and lecture notes. I'm not very in the favor of lecture notes because they are very different from different source, and if somebody want really to study the course, that will be a little difficult. So I prefer to fix a textbook, and that the textbook you have already, I send you the ebook. But let me know if any of you have a difficulty with this textbook, or you cannot, you don't have the device actually to read it, then we will find a solution for that. Because I can find a hard copy maybe from main library. Just because we are recording, so please let me know if anytime you don't see my screen, just let me know, and just by turn on your microphone, please let me know. And if you have a question anytime, please feel free to interrupt my talk and ask the question anytime. All right. We go to our business. So the businesses today is about the second chapter. So in first chapter, we read some basic information about luminosity, about the star formations, some introductions, and we listed also those four differential equations which they are needed to study stellar formation. As you remember, one equation was related to the hydrostatic pressure, gradient of pressure. Second equation was just mass continuity. Third equation was related to the actually read it like the change in the luminosity, and the number four was somehow was a equation for the gas, ideal gas actually. And we mentioned here that to find a final stage of the star, you needed to solve those equations analytically and numerically. So today we are going to talk more about how the stars are forming and what is the process. The process which the star formation is called a collapse. It's very complicated actually phenomena. Sorry, and it has a lot of assumptions and a lot of considerations you have to consider to be able to describe the final form of the one star. I want to tell you that as we mentioned in the first chapter, star formation is started by the cold clouds of the gas or particles, and the dynamic of such system is very complicated. So there is also one thing which we have to know, that is that when this collapse will start, when this competition between gravitational force and gravitational force actually when turn on, and started to attract the particle and collect the particle in one pack, which we call it collapse, and we will talk about the dynamics and the mathematics of this. So finally, the case which we will see is a compact object with some mass, and this mass could have a minimum and maximum or upper bound or lower bound mass. For example, before 2003 or 4, for example, for a family of compact stars, which we call it neutron stars, and later we will talk about them in chapter 7, I think, or chapter 8, in the last 2 chapters. People was understood that the mass of the neutron stars is bounded by somehow like 2.4 or something, and the 2.4 of the mass of the solar mass. But after more observation, then this bond changed. I want to tell you that the upper limit means that the maximum or lower limit means the minimum mass of the star after the collapse are very different, and they depend to theoretical models, as actually they also depend to the observations. What we say observation, what you understand from first chapter is that we can get some information about the effective temperature and about the luminosity, yes, for the main sequence star. So those two information, or those two set of the data, actually they are using to estimate and to find out more information about the other other parameters in the equation. So to see what is the collapse, I want to show you a simple simulations which done. So I hope you will be still with me. So let's go and watch it. Oh, I don't know. The works to copy the link. If you have any things, let me know any questions so far. So this collapse is very complicated process. I want to show you that. Okay, this is a means that you know that we have a model. For example, we write some equations to model, and we let the process start by a sample of the numbers. For example, here in our case, we started by, for example, 100, for example, particles, which they are a member of these starting clouds of the particles. Then when the collapse started, I want to show you what is going to happen when the collapse. This collapse of Rambash, they say, Rambash is a, I don't know, it's maybe Arabic word, I don't know. But this collapses means that they are trying to be close and close to each other because of gravity, and because of gravity is attractive. Let's to see this simulation. Look, this collapse. Look at the curve which will be happening. You know, at the beginning, you know, the structure was very regular. So then you see that it will be mostly curve, and then all the joint to each other, and then it gives you the idea of the collapse actually. This is very realistic. I mean, never the particle in the clouds will attract to each other like that. But it is just a good approximation. And if you want to see a more video about star formation, I want to show you a better one. Maybe it's more better. It's just okay. This is I mean here they consider the temperature, they consider the realistic density of the initial particles. So this simulation, that simulation was cartoons actually, and this simulation is a little bit more realistic. And also we let the time to evolve here. So let's start it. So this is we are starting from the when we have just a cloud of the cold particles. So now our time is 0. I mean, we are at the initial, at the beginning. So, okay, and this is something will happen in the distances or in the dimension of 80,000 astronomical units. So it's a very large distance, and we have this colorful, shell, this colorful spell. So different colors give you different densities. Okay, this is the idea. So because you have a different elements, light elements, and they are starting to collapse. Let's just see what is going on. When the collapse is started, after some time, you will end it with the different islands. So this is, in the Mysteries of Universe course. These different islands is like a gas, because different point in this system has different density. It looks like you have a different part in your gas. So then the process which is happening here is fragmentation. All of them are complicated actually. The spin is different fragments actually is based on the existence of some type of the angular momentums. And finally, state what you will see in the next 20 seconds. In next 20 seconds, you will see that after all those, the time is now 250,000 years. It's going to be 500,000 years, around 300,000 years. This is the perspective that you see. So that simulation not completed, but anyway, gives you the just idea that the dynamics is difficult. The dynamics of the particle, which has started this process of collapse, are very complicated. What is the difficulty about these gravitations and the role of gravitation in gas clouds? The difficulty is that this gas, this system of molecules at the beginning are out of equilibrium. What is the equilibrium? What is the equilibrium? Can you tell me what you feel about and what you understand when somebody say a system is out of equilibrium? What does it mean? Equilibrium is the phase of the matter when everything. Yeah, tell me.
The external force, like the net force, is not zero.
If they show you two pictures, for example, of everything, like the people, for example, in the, I don't know, the cars which parked in the parking, for example, or the people who are sitting in the cinema, for example. How by looking on the two pictures you can tell me which one is equilibrium and which one is out of equilibrium? I want a very physical intuition about equilibrium, and then we go to the gas. Well, what is bring to your mind when we talk about equilibrium and out of equilibrium? What does it mean?
Maybe there is some kind of motion or changes occur in the system which is out of equilibrium.
Yeah, out of equilibrium, yes, almost correct. You know, the out of equilibrium means that yes, you have a disordinary, or you have some external force, or different part of the system has different parameter from the other parts. But equilibrium means that everything is in the peace. So peaceful situation means equilibrium. We have equilibrium world also in markets. We have equilibrium in politics and everything. So it's very general. For the thermodynamic, for the gas, when we say a system is in equilibrium, means that all this interaction ended and finally the whole gas has reached a constant level of the temperatures. Okay. The problem with self-gravitating gas, or when we have a system of the particle at the beginning and they started to collapse because of gravity, is that they are out of equilibrium. So the situation which we are looking for is that at the end, the star which we will see should be at the equilibrium. This is what we want. So we want a stable situations at the final. Because first situation is very chaotic. As you see, I show you the second simulation. You see, it is very chaotic. So you cannot predict that, for example, which part will be spinning around the other one. You know, it was completely chaotic. And that was not because artistic video. It is a real, actually, because number of particles large, interaction very different. So when you have a number of particles, very large number of particles with different interactions, so the dynamics will be chaotic. Okay. So when we talk about self-gravity, means force which between different parts the gas. The thing here is very interesting. Of randomly moving, and if they have a tiny mass, so this tiny mass make somehow tiny mass affect the Newton law. So different tiny mass part in your system, so this part and this part, they make gravity together. And because the density of the matter at beginning is different, so different part of the system, this sphere is very realistic model. Again, I want to tell you, it's not really spherical symmetry. We make life easier just by considering this type of the symmetry. So different part of the matter in different point in the sphere has a different type of the gravitational mass. For example, I will ask you very interesting question after 2-3 slides. If you consider a thickness, a shell of the mass, actually, which this is a very tiny part of this whole system, and the thickness is delta x, and the radius of this shell, for example, is x. So the mass which existed between these two rings, actually, it is a sample of the mass of the whole mass. You can make this ring, and just you can make it a sphere. And you can make a disk, actually, if you look from 2 dimensions, because we look from the top now. We don't see the sphere. You see just here a circle. But this is a sphere, actually. So what you see here is the picture of the sphere when you project that on the plane. The mass which remain between two tiny shells with the thickness delta x is delta m, and this delta m, it can be easily calculated. If you know this from physics 1. If the delta x is the thickness of two spherical shell, and if the density is rho, so then just multiply the density to the thickness, multiply to the area, you get approximately the value of the mass which exists between two rings. Okay, and you want to consider this delta m like a piece of the mass which existed at the beginning for these clots, and these clots want to collapse and make finally one star for you. What is the total mass? So if you make the same model same model means that you just make a slicing the sphere, slicing this sphere with the different rings like that, called centric actually this rings, the rings with the same center. Then each area between two rings has this delta m. So you have how many of them you have? You have a large number of, large means infinity actually. So if you add all of these tiny masses, you get the total mass. So this MAR gives you the mass which exists at the distance of r. What is this r? R is changing also, yes? Before the star form and the final stage and reach the final radius, the r is changing. R is started from 0 to the any numbers and finally will be fixed somewhere. Do you know where the r will be fixed? Which condition fix for you the radius of a star? Do you remember? I said that in my previous, if you remember. There is a condition that if you impose that conditions, you will get the final expression for the radius of the star. Do you remember that? What condition gives you the radius of the star at the final? This r will grow, as I told you, will start from 0, go, and one day will be stop, one time will stop. What is the condition that after that the growth of the radius will stop? Okay, we talk about the internal, these particles inside this cloth has a gravitational interaction. So they make internal pressures. What is the external pressure out of that? When all this process and there is no pressure outside. So the condition which gives you the radius of a star is that finally the internal pressure will be 0, or technically say vanish. One day the pressure will end and then you will see you will see the star with the expected or with the what number as a radius. For example, just I want to tell you that just making a graph instead of writing on paper, just I make for you a graph. For example, you don't know, but I tell you that, for example, this is the pressure, for example, R minus sinus very complicated expression. Just I want to give you the idea of this is, for example, the radius, the pressure versus the radius. So I mean, by solving those equations we present in the first chapter, we get this expression. So I want to just plot that. I know that the radius should be some numbers which is not 0. Yeah. So R will start from 0. I don't know, to let I write 10. See that in this case, this R will be increased. Where? It will be increased forever, actually. So this model, I want to tell you that could not be the pressure of the stable star, because it will increase by R. Never will end, never will vanish the pressures. So, I mean, if this will be solution for the question which I presented in the first chapter, it could not be end, finally, it cannot be end to the stable star. It will be increased forever. But let's just make it for example, let's to see that if this is a pressure, what happened, for example, if this is the pressure, so then let's see what's going on. You see, look at that. So we see that, of course, that is not also a very good one, but anyway, it's yes. This is what you see that those type of the pressure equations, those that cannot be also 0, no? Okay, the first one was better maybe. this, for example. If they give you this as a profile pressure, you see that somewhere it will be 0. So if I click here, for example, I can see that this star can be formed with the radius around, for example, between 4 to 6, huh? It's before 4.5 can be the radius of the star. Of course, there is a possibility to have a star also with the radius around 3, you see? And there is also a possibility to have a star with radius less than 2, but here the pressure will be divergent. I mean, such analysis gives you the idea of what is the R, the radius of a star. So, if you consider a system, a gas system with many particles, you see the gravitations act as a fundamental force for you. And you can always write expression for the mass at any distance. At any distance. Can you tell me that? Can you tell me that if I fix it here, the final radius of the R star, what will be this M? How you can interpret this M? That will be what it will show to you if you continue to add this tiny mass up to the final radius. It will give you the final mass. To see that just how those equations are interesting, for example, here again, I want to, for example, this equation gives you the radius at any distance. Huh? It depends to the density. If I give you the density, you can put here and just integrate. Huh? Let's see, for example, one example. For example, I give you the radius, for example. The density is, for example, 1 minus this is the density, for example, 1 minus exponential x. And then we want to find the mass. So let's just see what is the mass. So the mass equation, m function of r, for example, is integral. Huh? I told you, you don't need it to, you can use any software or even you can use hand, but just I want to make familiar you if you are not very in the favor of the computations. Okay, integrate this expression 4 pi rho x squared from where? From x from 0 to what? To r, for example. Huh? This will be your mass. And then it is interesting to, for example, to plot this mass over it and see what is the relation between that is, for example, the expression for your, maybe this 10 is very large. So this is the mass. So it shows that for example, those I think this is plus expression, maybe not very good idea because okay, this is better. Let's to see. Because I just write the example by myself, so sometimes I find, okay, this for example. Look that, for example, this is very interesting, and it gives you, for example, the idea of the mass, which you can have between 0 to 0.5, for example. This number a kilometer, you know. I want to tell you that even not now in the calculation on if you want to do a small project in this course, such numbers has units. They are kilometers. Yeah, this is actually 500 kilometers, for example, like that. But we write 0.5. All right. So you see that all the equation here you can handle by the software. You can do it. The interesting slide for me is this slide, which gives you the acceleration, the gravitational force, or actually between two layers in this gas. So if you have a layer with thickness delta R, so gravitational pressure in one side is P, gravitational pressure in other side is P plus delta P, and the mass between this tiny slice is delta M. So this equation gives you the gravitational accelerations. And as you see, gravitational acceleration depends to the mass at the distance of R. So let's to see, for example, if you remember that was the distance of the R, that was our M. So I want to replace this M here in this equation and plot just G. So I can write just, and let's to take G. We don't need to keep this always. So I just want to plot G over G, what is called scaling. So this is my M. This is my M. So I divide this by R square. This will give you my G. Then I will plot the G. So I will plot the G just to see. This is the G. So it shows that the G will be, any other range. It shows you that the G near R0, G will be very large because R0 means the center of the star. You do not have much information about that. And then by increasing the R, for example, the gravitational will be increased. So if they ask you to find the gravitational accelerations between two layers, for example, in any planet, this equation gives you. Any question? All right. I want to, and then go to next slide. So if I ask you exactly what is the difference of the pressure between two layers in this system of gas or particle or molecules, this equation will give you delta P. For delta P is actually the gradient of pressure multiply the differential force. So this is, do you remember, this is like F prime X. F prime X is just df dx multiplied to dr. So F prime X is nothing, just F prime X, you remember, it's just df dx multiplied to delta x. This is, and you see that this is very general equation in the mathematics. First approximation, that is gives you the pressure gradient. What about the force? Okay, the force which exits over this, so if you are standing here between two layers, how much force you feel? This is an important question, gravitational force. This is a little difficult to calculate. To calculate the force, you have to consider the force which comes from the upper layers minus the force which comes from lower layers. The difference between the force which comes from the top on your head and the force which comes from your ground, for example, to your standing point, this difference gives you the total force. Do you remember what is the relation between force and pressure? Pressure is force per area. Area is A here. So just writing the force with upper level. For in upper level, you have a pressure which is a little bit more than the lower. And the down, you have just P. So if you write the P plus delta R delta A, this is the force came from the upper layer. And minus P delta R, this is the force which came from lower. So if you just subtract them, then you get delta P delta A. What is delta P? Delta P is gradient. Delta P is gradient of the pressure multiplied delta R. And what is delta R delta A? This volume. Area multiplied thickness is volume. So this equation gives you the pressure, the force. Yeah, this is the force from by the effect of the pressure. And because you have a gravity also, the gravity also make a gravitational force, mg. G is G, but instead of the m, you have density multiplied to volume. Then this expression 2.3 is the force which somebody feel if the person standing inside a cloud of the gas. I want to raise an interesting question here regarding this equation is that if, for example, this question is very fundamental. This is the question, so from this equation you can get the force which you feel in the airplane. When the airplane is flying, yes, you have a layer of the gas in the top and bottom, yes, and you have a size for your airplane. So actually, this equation of F gives you the force which everybody or everything feel inside the airplane. Of course, there are some other parameters, but I want to tell you that when we talk about the gas and gas particle, it means any part systems. This is approximation, but good approximation. You remember the force was mass multiplied to acceleration. Acceleration is second derivative of r. You remember? First derivative of r is velocity, second derivative is acceleration. If you multiply mass to the second derivative, gives you force. So this equation divided by delta m, which is the mass between the layer, gives you the acceleration. So this is the acceleration. Why this minus comes here? Because pressure force is in the opposite of the gravitational force. When you push something, it wants to reflect. It wants to push you back. This is actually somehow is like a Newton's third law also. This minus is mentioned that this pressure force works in opposite direction of the gravitational force. And from here we get that dPdr must be negative always. Okay. This equation is very important equations, and if you just tell me what is the pressure profile and density, I can integrate this equation for you. One of the projects which I want to suggest to somebody to study, of course, two examples we will see now. One example is when G is 0, and the other example when density is constant. Then you will see. But one of the projects which I suggest somebody do is that going through this equation, which is equation of the effect of the, which is equation which gives you the accelerations in the different layer of the gas, respect to the pressure and density, and by considering the gravitational accelerations, and just study the trajectory of particle, how the particle will move when the particle is subjected to this type of the equations. I want to raise a question here before I go and show you the examples. So just let's talk about this slide, and then, so this equation is very fundamental. The equation will give you gradient of pressure, which is negative with respect to the gravitational acceleration, with respect to the acceleration of particles. Okay, so there is a competition between the gravity and pressures. And finally, these computations will continue up to what time, what stage? Up to what stage these equations you have to solve, and how much information you need from. You have to continue up to the place that the radius of the star will be fixed. When radius of the star is fixed, pressure will be zero. Then this is the final stage of the star. There are solutions for this system. One of the solutions is that we consider that one of the solutions which we can find is that we forget about the change in the pressure. For example, we consider, we suppose that this is a hypothetical. Actually, this is very realistic. Realistically, for example, just to make life easier, we say that, okay, pressure not doesn't change very much. So in this case, dPdr could be zero, and then you will end with easier equation. And second second situation is that those terms will cancel each other. I mean, the gravitational actions, when the equation comes from the gradient of pressure, they cancel. So the second situation is that d2dr will be zero, d2dr. First example is called as free fall when dPdr is zero. Second situation is called hydrostatic equilibrium, when both of the terms will cancel each other. For free fall, for example, if you forget about the gradient pressures, you have to end to solve this equation. And this equation is very complicated. This is a differential equation, gives you R versus time, and you need also to have the mass profile. If you give me the mass profile, I can solve this equation, but not always is easy to solve. It is possible, as you can find in the textbook, that if you suppose that the density of matter doesn't change very much, then you can integrate this equation and you can find it something which call it free fall time, the final time which you need to wait to reach a final stage of the star. It's very interesting, yes? Those numbers you remember and show you in the simulation, 263,000 years, it could estimate it from here. I mean, if you set some good sigma rho here, then you can estimate the time which you need to wait to see a star is born. It's almost around some 100,000 years you have to wait by this approximation that you forget about the change in the pressure. The second approximation is that you forget about the two last terms. If you make hydrostatic equilibrium, hydrostatic equilibrium means that these two terms cancel each other. If you just rewrite the equation in better form, then and replacing the g, you remember what was the g? G was this expression. If you just substitute equation 2.2 in the expression of here, then you get the negative you get a negative value for the gradient of the pressure. This is called hydrostatic equilibrium. There is no accelerations here, so it's like no acceleration. It's like moving with a constant speed, for example. Any questions? I want to raise a question here regarding these equations. Do you hear me all? Because this is very important. I want to give you Okay. Listen to me. I want to ask you a question. I don't know how much you are familiar with science fiction, sci-fi literatures. There is a interesting books which is called Journey to the Center of the Earth by Jules Verne. There's a movie about that also, Journey to the Center of the Earth by the Jules Verne. So this book, I mean, there is some movie also built of that. In this book, the Jules Verne make questions, say that it is possible to travel to the end of this Earth by making a tunnel. You can start it to make a tunnel and go down, and then he claimed that you will end with the other world or other life or other universe at the center. Forget about what's happening for the temperature when you go down. Just imagine that you make a tunnel, okay, and you enter the tunnel. I want you, based off this equation, based off the original equation, I say, based off this equation, I want you give me a model for me that if we suppose that the pressure doesn't change very much when you go inside, that is correct, huh? Because you feel the pressure usually when you go to the mountain. If you know when you go to the mountain, your ears will be blocked, huh? You feel like a deaf guys, deaf people. If you go inside the earth like a planet and make a tunnel, then I want you to tell me that if you enter this tunnel, what is happening for you when you get close to the center. And I want you to judge that what the Jules Verne say in his novel is correct or not, what you think about. Everything comes from this equation. I mean, consider yourself as a person who enter the Earth, a tunnel, and just consider Earth as a planet with constant density. Then you can write this equation in the suitable form, and then I want you to give me the idea that what is happening for you when you get close to the center. That could be a mini project with somebody if you want to do. Otherwise, I will include this like a homework for everyone. So two situations or two cases from the equation of the accelerations is very important for us when you are entering or when we are studying the star formation. The first situation is the free falling, when we consider the pressure almost constant. And second situation is that when you consider hydrostatic balance. Hydrostatic equilibrium or balance means that those two terms on the right hand side of the equation vanish or cancel at each other. Then you will end with the equation which is written here as a gradient of pressure. Do you remember we talked about the virial theorem in first chapter? Virial theorem gives you the average of pressure and average of density without any knowledge about what is going inside. In next slide, which I don't want to focus very much on them, because you can see in the book, it is possible to show that the hydrostatic equilibrium leads to virial theorem. It is just to show that this equation gives you the same predictions as we can get from the virial theorem. You can just make a simple algebra, just write this equation, rewrite this equation in the following form. Put whatever related to the pressure close to the pressure, and put whatever related to the mass like radius here. Then writing the expression of 4 pi r square rho dr as dm. Remember, the mass is volume multiply the density. If you back the first slide, you see that the mass means little mass. Little mass was 4 pi r squared dr or x squared dr. If you use these expressions, instead of the what is written here, you can write delta m here. Then just by simplifying the equations, I mean, keep whatever related to the p in one side and keep whatever related to the m in other side. Then, and by integrations from the 0 to the final radius of the star, you will get these expressions. On one side, you will find the integral, which is gm dmr. This is energy, gravitational energy. On the other side, you'll get something is like a thermodynamic. Pressure multiplied to volume. And finally, if you divide this by the total volume, so you will get the average of pressure. This derivation is interesting, a little bit technical. So don't be worried very much about these derivations. So I want just to mention here that the virial theorem, which gives you idea about the average of pressure and density, is compatible with the hydrostatic equilibrium. Even from the information of fundamental physics, you can get this expression, but not very easily, but you can get that. So, virial theorem, so actually gives you the idea about the stability also. You have to know that the gas which we consider here are very relativistic gas, because they are burned, this particle are burned during some other nuclear reactions or other whatever experiments, the larger scale, in the deep space. So they are mostly very powerful. And they are very fast particles. When they are very fast, we call them relativistic. Something will be changed in our on our analysis, but we don't go through that. But we can say that relativistic nature of the particles which are involved in the star formation process change many things. Also, it changed the virial theorem. And when we say relativistic, means what kind of relativistic? For example, the particle could be very, very fast. This is called ultra-relativistic. They almost like a photon, but they have a little mass, like neutrino. Or they could be totally slow and lazy, which we call it non-relativistic. For both of them, the pressure will be a little bit changed, and this expression which we give as a virial theorem, which is for non-relativistic and classical gas, that will be changed if you consider the particle like neutrino or some other fast particles. They will be changed. The detail of them are depend to the chapter 21, I think, from the Physics Holiday Resnick. When you talk about kinetic theory, you can find some more information there about the relation between pressure and density for based of the kinetic theory. Virial theorem, which gives you the expression between the average of pressure and gravitational energy, help you also to estimate the total energy of final stage of the star. I mean, the star finally will be a compact object with a definite mass and definite radius, and it could have some amount of the energy, as you know. What kind of the energy will be? The total energy will be this, and if you wanted to calculate that, actually you needed to have some information about the virial theorem. Based on the virial theorem, I can tell you that For non-relativistic case, you can say that the total energy for non-relativistic case, I mean when the particle not very fast, is given, it will be just minus of the kinetic energy. The total energy will be negative. So negative means bended. The system will be bending. So the system looks like hydrogen atom finally. Star will looks like hydrogen atom finally. The energy, total energy will be negative. Because it's all gravity, and gravity makes always negative energy. As it makes also not only negative energy, as it always make contraction or attraction. This minus is actually related to gravity. And if you consider, and you can write also this in terms of the gravitational energy, because Virial theorem, again back here, Virial theorem gives you the expression of the average of pressure versus energy. Gravitational energy is related to kinetic energy. Total energy is kinetic energy plus potential. Potential means gravitational energy. By combining these two equations, you can find that the energy of total and non-relative case, I mean when the particle not very fast, is half of the gravitational energy. But this is a rough expression, and this is very rough estimation. I mean, it is not very, before you know something about the statistics and mechanics or many body systems, this estimation is not very, is correct, but is not very much easy to understand actually. But you are most welcome to ask me anytime about any of the concept which I'm talking during this lecture. So you can always talk about everything and don't be scared. So you can ask me any questions. If I know, I will reply you from the beginning, even from the fundamental physics. If you have a problem, just let me know. Actually, the what I planned was ended now. Just do you want it to talk about this equation a little bit? I want to give you the idea about that. So these equations is actually give you the acceleration versus the radius. So I want to write a model for the mass, for example. I write the mass, for example, here, mr, for example. I write the m like a constant, like rho multiply to what? Rho multiply to volume. So 4 pi r square. Volume. This is the volume. Yes. Okay, because something remained in the memory. So let me do 4 pi r square rho is your mass. If you are standing at any density, any distance r, I suppose that the density is constant. This is a little help to the question which I asked you. You are entering the tunnel, so the mass which you feel is like this. So if you write these expressions minus the differential of r versus time, second derivative of time, this is the second derivative of r, equal to what? Equal g multiply to that over r squared. Okay, so okay, sensitive to the indices that we used before r. Okay, this is the equation, for example, minus dr square is equal to that. This is a differential equation, gives you r versus the time. And I want to tell you that you can solve those equations and give the trajectory. So just you can use the software, and I don't recommend even software because those equations are very easy. You can solve it. You see that the solution comes like a periodic solutions, and you can also fix the parameter and make it the plot for that. So this is actually looks like a periodic equations. So I want to give you the idea that if you enter a planet, it looks like you are bent to the spring and you go and back around a fixed point. Okay, I stop it now because I don't want to run the course, so I will stop it there. So if you have a question, you can ask me. Otherwise, I will try just to make a PDF and share to you this, as well as the still, if you have the question about the project, those things, and then okay. Starting October, I'm Julia. Forever, if healthcare, yeah, I know this information. But if you don't have a question, I will.